And we're unpacking K. And K has a few things associated with it. Some things like temperature, right, is in there. Activation energy we talked about. And collision. How many times something interacts and the orientation of that interaction. Those are the two components that are wrapped up in K, and they're represented with Arrhenius' equation. And that's what you see here. So we'll call A the frequency factor, and we'll unpack that a little bit. And we'll call this E to this power here the exponential factor that has temperature, the universal gas law here, which is 8.31 we're using, and then the activation energy. So ultimately, when this exponential factor is higher and or A is higher, what does that do to K?
Makes it higher.
Makes it higher. And what does that overall do to the rate, to put this in perspective? It increases the rate, so you speed up the rate. So then what would you expect if I increase the temperature, would you expect the K to do, and therefore what effect would you expect on the rate? It would increase, right? So that means, in case you're not clear on this, this area here, e to this negative power, is essentially what? The inverse of the natural log.
The natural log, yeah.
Right, that's what that is essentially. So that means it has a range of what numbers? What is the highest and what is the lowest that I could have wrapped up in the exponential factor, not including the A?
From 0 to
From 0 to
infinity?
1.
1, yeah.
If this goes to infinity, what does this do? You can put it in your calculator, right? And if this goes to 0.00000, the opposite,
Sure.
what does this number become? What's the great? So the greatest number you can have here is 1. The lowest is 0, right? So you would. So when this piece here, the temperature increases, that does what to the exponential factor? It should
Increase, right?
increase it. When the activation energy increases, what should it do to the exponential factor? Decrease.
Right.
Because, and that should be intuitive, when the activation energy is lower, you're going to have a faster rate because things could move faster.
Exactly.
Okay, so what are we doing? We're looking at how K affects the rate, and more specifically, the things involved in K, how intellectually they affect it, and then of course we could go ahead and do quantitative analysis using this equation here. Okay, does everybody have a sense of now why K has an effect on the rate here, and why?
Just want to know why that gas constant is in the equation.
So here's the thing, I could spend a couple days going over how to derive this, right? But that's not what I want you guys to know. That's not relevant. All you need to know is what the major things are that are going to affect it. Now, the R is a constant, so that has no real bearing here, other than it's necessary to fulfill this part of the equation. And how to use it. So if I gave you a temperature and I give you this, maybe you could solve for K, which then allows you to solve for more things related to the rate.
So the reactants don't need to be in a gas form for you to use that equation, right?
The what?
The reactants would need to be in a gas form for you to use that equation.
Do they? We're talking about interactions. So I could take you, and I brought this up before.
With liquid.
If they're solids, are they gonna do anything? No.
No.
What do they have to be in?
Yeah.
Gases.
Yeah.
So we've talked about those things, right? So in an interaction, they do have to be in gases.
Right.
In fact, even more than that, if you go back to Chem 101, what happens in the gas form?
They're hitting all over the place, right?
The more times they interact,
More change.
the frequency factor and the orientation. That's all wrapped up in A.
Right.
So absolutely. And what is this called? Where's his name? So have you seen him before? Or his name before?
Yes.
Yes, and what?
Arrhenius acids and bases.
Uh-huh. And so he did a lot of work, and some of it is in gases. A lot of the stuff that a lot of these guys did started with gases, because that's where you're getting interactions from usually. So taking the big picture, looking at Arrhenius equation, within the rate law, how it affects the rate and the different things associated with it, because I could ask multiple choice questions and just simply say, well, what if I increase the temperature, decrease this, what happens to the rate? And then you have to correlate how this fits here and within this. But it also might allow you to solve for some other things associated with here, right? And there we'll do some tricks and different things on how to solve specific components related to this here, and specifically related to K. So that if I was trying to do so, well, let me take a step back. What's the relevance of this? If you're sitting in a laboratory and you want to know, you want to speed up or slow down a reaction for some reason, why would you care about this?
To let you know what things you can alter to make that happen.
Absolutely. You may not be able to do that, right, depending on technology or whatever, but at least you could assess, well, what can I potentially manipulate to speed this up or slow this down so that I could see it and figure out my results. If I want to try to determine, let's say, how a particular reaction will change to get certain products that I now want to sell to a company.
All right.
Okay. And I say, well, I want to make it as fast as possible without making mistakes. So maybe I want to speed up the rate of this reaction, and I already know the rest from experimental data. So now I got to figure out how to optimize K through looking here and trying to make adjustments so that I could do that. If I increase the temperature, is it always going to change something? Is it always going to increase the rate?
K, yes. Since it's on the bottom.
But can it sometimes have an effect on the activation energy? In a biological system, if I raise it too high, how could that potentially affect a catalyst?
Could it
I'm gonna
possibly
slow it down.
destroy it?
It could destroy it, meaning it can
Deactivate it?
deactivate it. It could adjust its three-dimensional structure, right? So just because I increase the temperature, that could also cause this to go away.
Right.
So then I'm balancing and I'm reducing potentially. So there are different scenarios that can happen.
So as like a regular example, lowering the temperature would make the rate go slower, so that's why you refrigerate stuff?
It would slow it down.
Or slow down the reaction?
Yes.
So that's why, for example, we refrigerate things.
Or like a
Yes,
fever.
sort of. I mean, so when you're dealing with food, right, you're just trying to preserve it.
Yeah.
So you could preserve it longer. In other words, you're also trying to fend off bacteria, and there are a few other things related
Like
to
fever?
it, right?
Fever would actually raise your body temperature.
What's that?
Fever would actually raise your body temperature to actually fight whatever bacteria
A
or
fever, you mean like a cold?
yeah.
So if you get a cold, you raise your
Raising
temperature,
Right.
and now you're provoking certain things to be activated. But it also potentially deactivates other things.
Right.
And you're so you're talking about a bigger system that's not just one, there are a lot of different components that are going
Right,
back and
right.
forth, so we can't say it completely.
Correct.
Because if I take something in a system that's being used for something, and now I divert it to being used something, even if I make more, I have less to do this.
Gotcha.
And what things am I stopping and slowing down? What things am I, promoting or speeding up?
Exactly.
It's hard to find that, which is the same reason why it's so hard to solve cancer, let's say. Because you have multiple different things. So if I know this one thing constitutively becomes active, this is what's causing that exponential growth of cells,
And that's what
right?
you wanna
The
do.
proliferation as opposed to differentiation. But then what are all the other things that I'm now blocking or
Right.
not doing that are also now, so if I stop this, do I still have recovery of anything else?
Exactly.
And that's harder to figure out, all of the things going on. So your systems that you two are talking about have more going on than just one thing. Okay. So we're using the R, 8.314 joules per moles K. Always use that in this context, which means temperature always has to be Kelvin, as you see here, and this is always going to be in joules per mole. Okay, so I think we've covered this. Now let's look into this a little bit more. A lot of the things we'll see now. So this is odd because it comes in a weird spot. And it's only one example to give you a sense of what's happening for just this type of system. It's just an easier way to explain what's happening. But I want you to think beyond this. So here you're looking at this thing here. You have the methyl group here connected to a nitrogen, which is triple bonded to a carbon. And over here, you have the methyl, which is now bound to the carbon and triple bound to the nitrogen. So the carbon and the nitrogen exchange positions. And they look at it like a wobble. Okay. In other words, it's one thing, just like we did here where we said A goes to B plus C, right? You're just looking at one thing, but in this case, it's just rearranging into this. So you can imagine a lot of times you're going to have two things that are rearranging and other things. This is just one thing that's adjusting. Just keep that in mind. And the idea here is that this thing, with enough energy put into it, wobbles. And you're looking at the end sort of twisting like this. And when it overcomes the activation energy, it twists completely and flips. So only a certain number will get to this that are able to overcome that activation energy. But the wobble trying to get there. Okay, and that's what this is representing. So this is really dealing with A, right? But in the context of A, you're looking at the exponential factor because you're looking at the activation energy and how that overcomes it. So we'll get back to A in the wobble. But for now, all you're really doing is looking until this actually makes the complete wobble switch. Then it's overcome the activation energy. That's all this is representing.
Okay.
And they use some fancy names. The methyl group, though, is for this methyl here.
Okay.
So, okay, let's look at an activation energy chart. You have the reaction going this way, which means you're going from reactant to product, and up here is increasing in energy. So traditionally, here's your product, here's your reactant, here's your product. The difference, if the product is lower than the reactant, what kind of reaction do I have? Exothermic. I've released energy from the reaction, which means it's now more stable, the products, as compared to the reactant.
Right.
But in order to do this, I always need to put some energy in, and that energy in up to this point is called the activation energy. And in this case, that's what's needed to create the wobble. So if you think of it like this, I'm putting energy in, some of these things are wobbling, the ones that get to the actual top and can come back down, get all the way to the activation energy, and then they come back down to here, where they're now more stable, and they end up giving back the energy I put in for the activation energy, as well as some additional energy as we call enthalpy, the delta H of the reaction.
That was actually one of the questions in the lab.
Is it?
As to with the spark. How
Okay.
come when you actually got the spark and then everything you just explode? So you have a hydrogen, oxygen, and oxygen gas. No, yeah, hydrogen gas and oxygen gas. They're just stable by itself in a flask, but then as soon as you actually introduce it to a spark, it just
Then it gets
explodes
the energy and
tremendously.
it goes through.
Right.
Now, up top here is sort of a hybrid between the reactant and the product. Okay, so keep that in mind too. That's also called a transition state. So more familiar that most of you have seen, most likely, is I have an enzyme plus a substrate, and I come through and I get to the activation energy barrier, and I see this transition state ES, and then it goes ahead and releases the energy, and I now have my enzyme free again and my product. So this transitions with the help of this to this transition state, which then produces the product. So this is more common in biological systems that you find in biology, in what you would see here. In this example, just another type of thing where I'm just rotating, and as it rotates and it gets to the halfway point, they're sort of showing this with the, so that's not a complete bond there. This is rotating. As it gets to this point, now it can come back down this way. It's also another, in this case they're calling it the activation complex. It's also called the transition state of the reaction. In this case, it's just one molecule. In this case, you're dealing with an enzyme. And in other cases, you have two different things that have come together, and they've made some kind of adjustment to an activated state. Okay, so this is the activation energy through here. It activates the transition state. By the way, the transition state is usually indicated by, just so you have this terminology, usually put something like this. And some kind of a symbol related to that. That just indicates that's it. You're at the transition state. That's all.
Like a not equal to?
Yeah, something like that. I think we'll see one later. If not, then you know that it'll help in biology, so you can understand that that's not the substrate. So in other words, these would be like the reactants or the product. Not when they're separated, but when they're connected. Okay, so I have the activation energy. I have the delta H. This is below this, lower in energy, therefore exothermic. What else do I want to point out here? I think that's it. You need to be able to look at one of these and identify what's going on there. no big deal. I think you had to do that in Chem 101 as well.
Yeah.
So what's this? Activation. Okay. So we talked about exothermic. If I was here and the products were higher than the reactants, then it'd be endothermic, because even though you had to overcome an activation energy, you got only some of that activation energy back, which means you lost some. That's an endothermic reaction. In other words, energy was put into the system. I think that's about it. Weird. Why are they doing this? What's okay? So. I'm going to say K is equal to A, and let's just say E with a bunch of stuff. I'll put it up just to make sure that this is clear. So here versus here are the two things we're looking at. And it looks like they're transitioning to the frequency factor. This is the exponential factor. They're transitioning to the frequency factor A. And A breaks down into PZ. And one of them is for the number of interactions, if you're looking at that, the collision theory. And the other one is the orientation. So if I hit it here, no big deal. If I hit it here, it's orientated properly, which is something an enzyme helps speed up. So as this gets higher, obviously, these two things, one of them or both get higher, this gets higher, that increases K, speeds up the rate. Okay, I'm not so sure they want to make that full transition here, but that's what this is representing here. The frequency factor. And they're just saying that as this thing wags, it moves with energy put into it, it moves towards the activation energy barrier, and once it overcomes it, then it comes back down. But the wag, not all of them make it. That's all it's saying, right? It will wag, come back down. Another one wag, come back down. One wags, gets high enough, now it comes back down to the product side. Okay. For example, one way to think about that would be if I have a stove that has heat coming in here and I put a pot in here. And let's say I have little H2O molecules here and here, right? Which one, so I have an average kinetic energy in there, right? That's, I take this water, I get the energy in this, energy in that, divided by 2. That's my average, that's my kinetic energy. Or what I also see on a thermometer, right? However, this one, is this one closer to the heat going to have more energy than this, or less, or the same? More. So different ones can absorb more energy depending on where the energy is coming from, and hence wag a little bit further and sometimes overcome this activation energy. Does that make sense? Just to give you a sense that that's why it's not like they all have the same amount of energy at any given time, the molecules. Okay. And most do not have enough energy is what they're going to claim here. But once again, that varies, right? I mean, that's kind of an odd statement, because the presumption there, like a lot of things that are in the notes, which I'm trying to deter you from at this level, is that it depends on a lot of factors, right? What if I did something to lower the activation energy of a system? Then I could have maybe at least half or more actually have enough to overcome that barrier. What if I increase the temperature so I haven't denatured the protein or the enzyme, and now more can go through? So it's not always, the generality of it is that most are not going to be able to overcome that. But I could change conditions and optimize conditions so that I can have the majority overcome it, especially if that's what I want in a laboratory for some experiment or whatever else. Okay, which is the whole point of knowing this kind of information. I could take this and I could use it.
So would putting an enzyme be lowering activation energy?
Absolutely.
Yeah.
Absolutely. It's exactly what it would do. You become down here. Sometimes they have 2 loops because you have different transition states from that. So it will usually look something like this down here. And of course, if I do that, then I can say most do overcome it, right? At a particular temperature. Which is why I want to make sure that the wording, it comes across as though there's some absolute. But that all depends on what you do, what your knowledge is, and how you make adjustments, which is the whole point. Okay, so that's why I said this is odd. This is just recounting, sort of bringing up the frequency factor, the A part, And then it goes back to the exponential factor. I thought it was a little premature to stop the exponential factor discussion at that point. So we'll go, be careful in the notes. Look at what it's doing. It's going back and forth between the exponential factor and the frequency factor. So you're going back and forth between the A and the E with everything associated with it. Okay, so they're going back here. Hey, you guys already know this now. The exponential factor is a number between 0 and 1, right? So this is it. So they're re-showing you this. Okay, so we've already covered this.
Is this not chapter 14 on the book?
It is chapter 14.
So low activation energy would be high temperature. Okay. Low activation energy and a high temperature make it make the negative exponent small, right? So that makes sense. Or does it? What would you expect? Forget about what this says. If I lower the activation energy and raise the temperature, what would you expect the E to do? Go to its highest number or lowest number?
Lowest.
Highest.
I mean the highest of
What
negative.
are the number range of the exponential factor? 0 to 1.
Mm-hmm.
So by lowering the activation energy and increasing the temperature, presumably it would do what? It would get closer to 1 and increase it. Okay, so that's what this is saying. It approaches 1. That should make sense. So
okay.
now we're going to look at the, this is why I said forget about the wording was strange, right?
Yeah.
Forget about the wording, just go with what you understand, what you would expect. Once again, not 100% of the time that's going to happen, because I could do something where I raise the temperature and I denature the protein.
Right.
Clearly now it's going to be harder to overcome that activation energy. So depending on extreme situations and optimization of protein and therefore enzyme activation would matter. So what am I going to ask next here without looking at your notes? I'm going to increase the activation energy and do what to the temperature?
Decrease.
Lower it, and what's going to happen to the number of the exponential factor?
Decrease.
It's going to go down closer to?
0.
Absolutely. No big deal. You guys already have now the knowledge to be able to figure that kind of thing out. Of course, those are nice little test questions, right? Multiple choice. If I do this and this, what happens? What if I increase the temperature and decrease and increase the activation energy?
Same, 0.
0? Approaches 0?
Absolutely, thank you. These do not always have, not everything is an absolute, right? You got to think about it. And how would you assess that? So over here, well, you don't know. It depends. What would it depend on? How much I increase this or decrease this, and how much I increase. So my example was I increase this and I increase this. So do I increase this more than this? Do I increase this just a little bit and I increase this a lot?
Gotcha.
What would happen? What would you expect, right? Think about those things. If I decrease this a lot and only slightly increase this, what do you think will happen?
So it's like just increasing that one.
I'm going to get closer to 1.
Right.
Right. So that's why over here it depends, right? Which is exactly the point. A lot of this depends. Even the ones that are guaranteed, right? That you think are guaranteed. This one goes down, this one goes up. It must get closer to 1. Okay. What if that deals with the catalyst, and that catalyst is an enzyme, and I denature that enzyme by increasing the temperature so much?
Yeah.
So I probably can't keep increasing this and expect this to go down. Maybe this starts to go back up at some point. Right? So you got to kind of think about what's happening and why. I'm only going to give you scenarios that are going to make sense to you, but in a lab, sometimes things don't make sense, and this is why. Right? You have to actually think about it, especially if it's something nobody's ever done before, working with a new enzyme or something like that. Okay. Somebody out here. This is a real odd chart. Okay. I'm not exactly sure why they show this in the book. I don't want to explain this. The point of this, when you look at this, so you're looking at energy and the fraction of molecules. Let's start with that. Okay. And they're setting where the activation energy is in this position here. It's odd because what if I shifted the activation energy? That makes it odd on its own. The second thing is you're talking about the same thing. These are not two different things. It's the same thing at different temperatures. right? So that's odd. I'm not, it looks like I'm looking at one set of molecules and another set of molecules. I'm looking at the same set of molecules under different temperature conditions. Okay, that's to make that clear. The one in red is has a higher temperature. That's all. So P2 is higher than P1, which means that it broadens out the spectrum of where the fraction of molecules are. And at the activation energy then, because it's more broad, you're going to have more of them overcoming the activation energy than at the lower temperature T2, which is distributed this way, and that difference is right in between. Okay, look at that on your own and see if you can figure that out. It's a little bit odd. The only thing it's saying is that at a higher temperature, you're going to have more things overcome the activation energy, simply because you have a greater distribution of molecules that have more energy in them. That's all it's saying. That's the. Other than that, you could try to figure out the rest. That's pretty much all it is. My argument there is, well, based on that, if looking at this, if I move the activation energy over here, what happens? I now have a greater distribution at a lower energy. But what would that mean in the context of what we already talked about? I've denatured the enzyme or whatever is promoting it, and that's why. Right? So there could be reasons behind it that may be or may not be why this particular one is, but that's not necessarily the point of this. They're trying to tell you, as all these books do, which I don't like, is that these things are preset and they all look like this, which is 100% wrong.
Right.
Right? Different conditions, different things matter a lot. Okay. So that's all they're showing here. Okay, so this is everything we've talked about, nothing new. And once again, the one thing I really want you to take from these lectures is not everything is an absolute the way it's described. I really want to enforce that, because as you get further on in your education, you'll realize every door you open, 10 more new doors are there saying, wow, what happened here? And that door that you open may not be exactly the same door that you're opening in this classroom. It's a completely different one because it's a completely different system it's set up, right? So that's just a summarization. That transitions us into reevaluating Arrhenius's plot, because one thing all we've done so far is intellectually understood and broken up what K is essentially. But we also want to solve for things so that we could put, actual numbers and say, well, if I did this, this goes up by this amount or goes down by this amount. And to do that, we use Arrhenius's equation by plotting it. Up to this point, we've looked at plots like rates, right? And first order, second order plots, stuff like that. So what do you think I'm going to do here? I'm going to find a way to put it into what format? A straight line? So I'm going to find a way to put it into y equals mx plus b. That's all we're doing here in order to solve for things like k, or a, or ea, or t. Okay, so that's all we're doing now is we're just taking something, we're going to plot it, we're going to put it in the format of y equals mx plus b. So of course I got to start with the equation itself and somehow rearrange it. If I have this here, is this easy to work with on a plot? What am I probably going to do to it? ln, right? Because this is the inverse of ln, so I'm just going to take the ln of, if I take the ln of this, I have to take the ln of this thing, so I'm going to have the ln of this and the ln of this, right? And then I'm going to set it up into a plot that gives me a straight line, y equals mx plus b. Okay. So there's the ln, that comes out, so now I've gotten that out of the e to the minus. And I rearrange it a little bit. I simply just move these two things like this and like this. And what am I plotting now? What's my x? What's my y? What's my m? Y is log k. Okay. So if I know the y, or if I know the x, I can solve for k in that context, right? Once again, it's not k directly. I got to take it's the log k. And y equals m, so there's my m wrapped up as a negative ea r. I already know this, so my m, if I know m, can I solve for this?
Yeah.
And x, 1 over t, and b. Okay, once again, makes it nice and easy to solve for all those things that you're looking for. So why would I solve for a? What if I was solving for a? What am I looking for? Frequency factor. A is the frequency factor within k, right? And then if I have a, and I can now also solve for EA, I would need to be, and I know K, I could solve for T. If I know any of the three, I could solve for the other one. Or I could break them up depending on what my actual equation is and solve for them by plugging in. And then ultimately I can get my K, and from my K I could now figure out maybe an actual amount of rate if I know my concentration and my exponent. Okay? There's that y equals mx plus b, nice and easy. So I'm going to graph that. If I graph it, what do I need to know?
You need to know what your activation energy.
Temperature and K.
Wait.
If I know K and I know
Okay.
temperature, so I still need to know data, right? I need to say at this temperature, this is my K, at this K, this is my temperature. I get the experimental data, I could then plot it, and now from that I could solve my EA and my temperature. So here's different temperatures in K, going from 600 to 12, then picking it up 1300 to 1900 by 100 increments. And here's my rate constant given by this. So for each thing. So I could take that and I say, look, maybe we should put this up here. No, we do that. Let's make sure that we can look back at the equation easily. And we can say log K equals log A minus, or let's go to the bottom one actually, so it's in the property one. Minus EA over RT plus log A.
1T.
Maybe I should separate this. Make sure that it looks the same. Is that easier?
Yeah.
So now I take this data, I can take 1 over T for my X, correlate it, take the log of the K, which is given here. Remember, K is called the rate constant. Make sure those terms aren't confusing. And let's plot it. There we go. So I do this in Excel now, right? And I see, is the slope positive or negative?
Negative.
Negative, how would I have known that otherwise?
The sign rate.
Negative EA over R, negative, okay? So I expect that. My slope is negative 1.12 times 10 to the 4th, and my y-intercept is 26.8. So that's great, that gives me a lot of information, right? I could quickly solve for A. What is A? Log A is equal to what?
26.8.
26, so I take the inverse log of this and I get A. Pretty simple, eh?
Right.
Okay. Let's say I want EA. How would I solve for that? This whole thing equals what?
Because they were negative 1.
M, and this is M.
Yeah.
So now I could solve for EA, because I already know R, 8.31. Okay. So here what it's saying, determine, so it actually asks us to solve some things. So determine A, EA, okay, there we go. Exactly what we just talked about, right? I didn't realize this was an example. I thought this was part of the discussion. Just kind of jumped into an example, huh? Was it an example here? Oh, I guess it's an example there. Does that make sense? How to solve for this? At this point, this should be somewhat routine. Where are the complications going to come from on an exam? So now you're going to switch back and say, okay, as I walk you through, yeah, this is easy again because we're doing something very similar to what we've done before. But in an exam, are they going to be nice and am I going to have something like, oh, we're looking at Arrhenius's equation, we're going to do Arrhenius? No, right? It's going to ask some questions that are going to come out of left field. They're going to be up. I might ask this before I ask something about a rate law,
Right.
and then a rate law. They're going to be juxtaposed throughout. So you got to quickly identify what is it you're asking, and then what tools do you have in what area? Oh, we're dealing with K here. How do I solve for K? I must be thinking of Arrhenius's equation. Do I have a plot associated with that, or do I need to make one or anything else? Right? So that's the complication, is that now you've done multiple plots. Which one do I use? When do I use it? How do I use it? On some question on an exam where somebody next to me is scribbling as fast as they can, getting everything right. And I'm increasing the tension of myself and everything else. That's where the complication here should be pretty straightforward as we describe it. And if it's not, then you need to ask to make sure it's straightforward before you leave. Then you need to be able to take it and say, well, if things were going to be thrown at me from this direction, this direction, this direction, this direction, then how do I figure it out, and what do I use to figure it out? So So here's what we said before. Here's M gives me this. I have that. I have M. And now I just plug in chunk. Just make sure you know how to use your calculator properly, right? Which sometimes is a problem, especially in dealing with logs.
Yeah.
Okay, so then here, and I solve for EA, and this cancels, so this should be in joules per mole, which it is. And that's the energy, activation energy, 9.31 times 10 to the 4th joules per mole. So what question should you have at this point? So if I was looking at this, I'd say, okay, that's kind of interesting, but what question should you have? Based on what we just did and what we're looking at. What are we looking at? What did we just solve for? Activation energy. So then what
Oh, is it exothermic?
what makes you curious? Yeah, is that a lot? Is that a little? What are the ranges? What's a high activation energy? What's a low? Does it depend on the system? Right? These are the kinds of questions you should be asking when you see something like this, right? To yourself. Okay, and we'll get into that a little bit more, I think. If not, these are still the types of things you would ask if you were doing research or something else, you know, from a scientific perspective. So 93.1 kilojoules per mole. In other words, what we don't have on here is, what is this for? Activation energy of what? What's the system? What is the
oxygen.
chemical equation that we're
The
looking
oxygen?
at, right? And then how does that translate to a different chemical equation,
Okay.
right? Certain enzymes. So the higher this number means that it's a higher activation energy, which means it does what to the rate?
Slows it down?
Rate goes lower,
Right.
because K goes lower. These are the kinds of things that you need to think about. So is that high or low for a general, let's say, a biological system,
Depends.
right? Are they all going to be the same?
No.
So I look at a cell, let's say a liver cell, are every single enzyme in there going to have the same rates?
No.
No, some are going to be higher, some are going to be lower, based on different things. Some you're going to have more enzymes for to speed up, some you're going to have less because you don't want them to speed up.
Mhm.
How do you know which ones are more active at any given time than another one based on external surroundings,
Okay.
right? So these are all different things that are at play within a biological system and also outside of a biological system. When you're looking at the interactions, you're looking at, well, what's the activation energy to make that reaction go or not go? Do you want everything to move forward all the time? Maybe, maybe not,
Yeah.
right? So it all depends. Okay, A, that should be pretty simple. Log A is this, take the inverse of log A, and I get 4.36 times 10 to the 11. What does that mean? Is that number high? Is that number low?
Right.
In relationship to
Frequency.
the way it interacts and the orientation of it. What would matter to the orientation?
When you say it's about frequency factor, is the reaction, or actually meeting
The number of
activation
interactions
right?
and the orientation.
Okay.
That's what it means. What's going to make the interaction, the orientation, matter less or matter more?
Temperature?
Would it? That would increase the number of hits. If I increase the temperature, am I going to increase the number of hits?
Yeah.
Yeah, because they're going to speed up, right? So that's, but then what about, does that change the orientation? I have a better chance of it properly orientating by hitting more. But does that increase the proper orientation? What would influence that?
Activation.
Enzyme could,
Catalyst.
different types of catalysts. What if it was just the things on their own? One-on-one interaction between an iodide and a hydrogen
Ionization energy.
versus a big molecule and another big molecule. Which one will have the
Surface.
proper orientation more often?
The surface
The smaller
area
ones.
as well?
Yeah.
Right? So you could think, right? These are some simple thoughts. These are not, that's not that scientific when you think about it. Even though that's tough to come across because as you're thinking of all these other things, you got to place them and understand, why does this matter? What would matter here? Right?
The surface area.
Surface
ionization.
area, absolutely, that's going to matter, right? We talked about that in Chem 101.
Right.
If I have things here and I'm looking at the vapor pressure, am I getting the vapor pressure from things down here or from up here?
Right. From up.
So if I take this and I make it more broad, so it's much smaller, am I going to have more vapor pressure here than here
Absolutely.
at the same temperature?
Yeah.
Right, things like that, that matters. So that's what you just said, surface area.
Mhm.
It's more exposed, can interact more. Where does that happen a lot in your biological system? Surface area, for example.
The ocean.
More specifically.
The ocean. Oh.
In a nucleus, what happens in a nucleus? What's in a nucleus? DNA and other things, but DNA is the more prominent thing, right? And how's that DNA? Is it
Okay,
just
yeah.
linear, sitting there, hoping
Helical.
something attaches to it?
Helical?
It's wrapped up in supercoiled.
Yeah.
And what do you need to do to activate some region of it so that it binds to it? You need to expose it. So you
Right.
need other things to come on, open it up, take it out of the histone nucleosome arrangement, right?
Right.
And once it's exposed, now something can bind, surface area.
Mhm.
That happens in a biological system. Okay, so, but it happens in other things too. That's just one example, just to put it in place. These are the kinds of things you should be thinking about in whatever it is your interest is and how it applies here. Right? It's not just one thing and only that one thing, whatever I show.
Nice.
Okay, another example, what do I have here? Use the results obtained in example 1, so what do we get in 1? A and EA. So I have A and EA, here's the equation. A and EA,
You got 93.1.
so obviously what,
Do you need them?
well, what depends, what am I, what is it? What am I solving for in the next one?
Because you're solving for K.
Am I?
You are so.
What kinds of things can I solve for if I have EA and A?
You can solve for K.
And for T?
Because you don't have temperature.
I
But
could
you're
solve for,
given
so if I give you one or the other, I could solve for the other now.
Yeah.
Right.
And you're given temperature.
Okay, so I'm given temperature, so at that temperature,
Uh-huh.
What is the K?
that's my rate constant.
Right.
Yes.
Based on this activation energy and that
Frequency.
frequency factor.
Yes.
Right.
And you can just use.
So everybody see why, how this works, right? So then they're gonna ask, okay, so they give me the temperature of 298, and they say, determine the rate constant. So they're asking for K. They give me temperature. I already have EA and A from the previous example, so I simply solve for K. Right, I just plug in and chug. Is that okay? No big deal? Oops, they don't explain. That enough? Everybody can do that on their own and see what answer they get. What should, you can figure out the units, right? Based on what's gonna cancel between these things here. And, A does not have a unit, so it should be, you could figure out the unit. It should all cancel out in this case. Okay. 3, anybody need any more explanation on 2? Go ahead.
I'm just confused on the A equals E to the 26.8 power, that you got like the 4.36
Here?
times 10. Yeah,
This?
what is that?
Inverse log gets rid of the log. Inverse log is this.
Oh, okay. And then that gives you.
And then yeah, that gives you this.
Oh.
So on a calculator, this is just one step.
Okay.
You just
4.36?
Your calculator, you either put 26.8 and then second feature ln, or second feature ln 26.8, depending. Okay. 3, reaction A and reaction B have identical frequency factors, okay. However, reaction B has a higher activation energy than reaction A. Which reaction has a greater rate constant? I'm good, I like this question. So this, you don't have to solve for anything in terms numerically, right? This is just saying, I have 2 reactions, A and B, okay, A, B. Well, both of them have the same frequency factor, right? And one of them has a higher activation energy. So let's say B has a higher activation energy than A. Okay? So which one, they have the same temperatures, they're both at room temperature, which one has a greater rate constant? A or B? A. And therefore, which one will have a faster rate? A. Absolutely. And that's because I understood where EA was within it, and since this one's higher, that made the exponential factor lower, and therefore made that K lower since the frequency factors were identical, and the temperatures are identical.
On the previous one, it said it would be 4.36, so basically there's no, like, nearly any effect on the activation energy and temperature.
Wait, when you say, you were talking about this example here.
The previous one.
So this is not in reference to the previous one, this is a separate one, right? This is not saying referencing experiment 1, this is saying you have 2 reactions.
Right.
Right. The question 2 was referencing the data used to get these 2 things from question
Oh, no, I
1.
mean, I did it on the calculator, and
Oh,
then it
you just
gave
have a
me
number?
Yeah, 4.36, which
Possibly, yeah, I didn't do it, but yeah, I'm sure that's right, assuming you did the.
so it really had no effect on the activation energy and the temperature increase. It actually didn't have any effect. in correlation to the frequency.
Well, you already, the activation energy is constant in that case, because you
Right.
found it.
Correct.
So then if you increase this,
Mhm.
you should increase this. If you decrease it, you just found 1 point there,
Right.
right? You already have EA in this. So he's going back to question 1 and 2, just to preface this. So if you have a higher temperature, you're going to have a higher Kelvin,
Correct.
or a higher K. If you have a lower temperature, you're going to have a lower K.
I know,
Because
I mean,
your
with
EA is
the-
already constant.
With the numbers that they give me,
Yeah.
that we actually use there, it's basically actually constant. Like,
That's what I'm saying.
just
The EA,
remain
you
there.
found the EA.
Right.
So based on that, it's constant. So then you're only looking at the interchange between K and T.
Correct.
So then if this goes up, that goes up, this goes down, that goes down, etc. It doesn't matter whatever number whatever number is given.
Okay.
So if I adjust it to 353K, which
Right.
increases it, then your K will go up as well.
Exactly. Okay.
Okay, so this one, getting back here, does this make sense? Everybody agree?
Yes.
A has the higher K, right, and therefore the higher rate. So you're looking here. So this one was higher in B, therefore this is lower, which makes the overall thing lower since these are the same, and that would be lower for A, and if this is lower in B, then this whole thing is higher than the A. Since it's constant, this also goes up. So the activation energy of B is higher than the activation energy of A, or BA, whichever one has a higher one. Higher activation energy means that it has a lower K,
Right.
and therefore a lower rate, so B is slower. Okay. I like that kind of question because that's more of a thinking question, right? You know, plugging in numbers is not that big of a deal. If you have an equation, you plug in numbers, so what? Understanding what it means matters more, right? And therefore when and how to apply it. Because in situations where you're either doing research or you're on a job, you always have the equation, but then you're asked at some point with your higher education to understand what you're trying to accomplish. So how you make the adjustments matters. Do I want it to be lower or higher? How can I make, so then if you make the wrong adjustment, then you probably won't be on that job very long. So you have to be able to think, what am I doing? So that's why this kind of question is much better than the other one, because the other one, you already have the number, you already plug in numbers, no big deal. Plugging in the right numbers matters. Okay, which way are you trying to make the adjustment to? Okay, so that leads us to collision theory. So now we're actually entering the frequency factor A. This is really where the frequency factor plays a more prominent role in the discussion. So I know we briefly touched on it at looking at the wobble, right, before the wobble overcame. So the wobble is just the number of wobbles in that case. A and B as reactants, how often they actually interact is part of the frequency factor. And then, of course, the orientation is the second part. Okay. So here, we looked at the wobble example, now we're looking at two different reactants to get products. And based on the collision theory, the number of times that they bump into each other, the better chance you have of them interacting appropriately and orientating appropriately. So I'm going to break up A into P and Z, P being the orientation factor, Z being the collision frequency, and both those two terms on their own should make plenty of sense. Frequency, how often they interact with each other, and orientation, if they're properly orientated to actually have an interaction.
Okay.
So look at P and Z, just the orientation factor. And the collision factor. Okay, of course we're dealing with gases, so the pressure, as I increase the pressure, what happens to P?
Faster.
You don't know. Not, you don't, that doesn't, you would assume that if I increase that pressure, that I'm going to increase the collision number of collisions, and therefore, as a result of that, I'll increase the orientation factor.
That's what it was thought.
Okay.
But you're saying not always? Or it is?
In general, that's a pretty standard rule,
Okay.
right? Because if I increase it to the point where I have more interactions,
Correct.
I'm likely going to have more opportunity for it to interact appropriately.
Okay.
However, it could, so just looking at the frequency factor,
Mhm.
if I then look at the exponential factor as a result of increasing that pressure, which I'm probably increasing the temperature to do that, right?
Right.
Then that could cause a problem with the activation energy by reducing, say, the three-dimensional structure
Right.
of, let's say, an enzyme or something. So even if my A goes up, if my exponential goes down, then but if I'm just looking at the collision and the orientation factor just wrapped up in A, the frequency factor here,
Then that applies.
if I'm
to-
isolating it, then that should pretty much almost always apply.
Right.
Right. Of course, if I denature the protein that the things that I'm interacting with, if it's a protein or something else,
Mhm.
then I may increase the collision, but what might happen to the orientation?
Different, right?
That also could
Different
go down,
result,
right. But the actual collision should increase.
Right.
Okay, this is everything we just talked about. I'll let you look at that. So here we go. So here we're looking at sufficient energy and proper orientation. When I look at this NOCl, so I have a nitrogen, an oxygen, and a chlorine, and as these things bump into each other, they form these things here. I increase the number of times they bump into each other. Presumably, I increase the number of products, which also usually is correlated with increasing the temperature and potentially decreasing the activation energy. But they also have to be properly orientated. So if this thing bumps into it here, is that going to do anything? Does the red ever mix with the green in the product?
No.
No, right? So if I'm bumping those things from this position to this position here, not a whole lot's going to happen. Even though I get an increased number of hits,
Refractions.
they're not in the proper orientation. What needs to hit each other?
With the green and the green.
So the green and the green would matter because then they could potentially come off,
Correct.
leaving those two things, and now I have
Yeah.
here. So if this thing orientates in a way that hits the green appropriately, and now they could dissociate from the blue and the red, I now have my reaction, proper orientation.
So
Surface area of the molecule and where they actually interact.
the ionization energy will be.
What if the molecule, like, or the atom is more stable in the molecule than it's in?
Then I might have some that start to come off and some that come back on, and I get transition states at the top of the activation energy. At that point, if it goes the other side, then I now have my product. If it comes back, then I don't, and the activation energy would most likely be higher if it's not a favorable interaction, all on its own.
So it goes back and forth.
Get hit, some are going to get to the transition state, some are not going to get to the transition state. They're going to hit all over the place. The ones that hit around here aren't going to do anything. And then these hitting in certain ways with enough energy could get up to the activation state, the activation energy barrier, and then they could reorientate from their transition state and come down as products.
Ionization energy is not taken in consideration in this case.
Yeah, but we're not going to discuss it in this context yet. Okay, so here's a real simple example, I guess, of what I just told you. So here, this would not increase the proper orientation, this would not increase the proper orientation, and this would very much increase the proper orientation, and therefore overcoming the activation energy barrier.
The orientation factor, if it's higher, does that mean the orientation matters more? Like,
It just means that it's more common that it happens,
okay.
not necessarily that it matters more for the K, because you still got to deal with the temperature and activation energy and the frequency.
Yeah.
As an example, I have these two things, and let's say they just float in some way where they could always interact, like this, versus not. And I take down the temperature, and they don't come near each other that often, and I have very few of them. And then I increase it so they bump into each other a lot, they do this. Right? So it not necessarily matters more, but. Okay, so one thing to point out here, some reactions have orientation factors that are much smaller than 1, which means that it's very hard to get that reaction to go forward, right? The higher the orientation factor, what happens to the rate?
Increases.
Increase, why? Because K
Okay,
increases.
right.
Right? I keep this up because I want you to really see the bigger picture of where what's actually happening to the overall reaction as a result of the things wrapped up in here. So we're going to keep the small, that's exactly what you do when you do research, by the way. You go through, you have a big picture, you try to figure something out. Then you get detailed, more detailed, more detailed, more detailed, to the point where you forget sometimes what the big picture is. What are you really doing it for? So I always take a step back and say, okay, why does this matter? How does it fit into what I wanted to accomplish? So, okay, then this be pretty obvious. I'll let you read this. Very stringent. To be aligned in a very specific way. Okay, here. So I have H2. It wants to interact with the CH2 double bond between the carbons. And in order for that to do that, this H has to come onto one carbon, and the other H has to go onto the other carbon. And that gets rid of the double bond there. Through SN1 interactions, you'll figure that out in organic chemistry, how that works. And I end up now with the CH3. Ethyl. I think it's ethylene. Or ethylene. And when I just look at that, when you looked at this kind of reaction before, even though it was usually written with formulas, not necessarily with the double bonds there, what would you think? How what?
Probably has a high activation.
Probably high activation energy, you got gas for gas, so you know that something's happening here. What else can you say here before this semester from your Chem 101? You'd say, okay, what kinds of things? Well, I have a chemical equation. This thing interacts with this, sort of, somehow, and I get this.
Right.
Right? Do I know anything else about this reaction? Well, I know that there's some coefficient, that's it's a 1 to 1 to 1. I know that this is a synthesis, right? Beyond that, you didn't know a whole lot, right, from Chem 101, other than it's a chemical reaction.
Wouldn't you also know that the pressure decreases, or the pressure increases because they're all gases?
So the question here then,
Or decrease.
you also, if I recall, you could figure out the liters, the volume, if they're all gases, right?
Right.
Using Avogadro's law, do you recall that? And you can say I have how many moles of gas on this side and how many moles of gas on this side. I have 2 moles of gas on that side and 1 mole of gas on this side.
Right.
Yeah.
So the moles of gas, did they go up or down?
Down.
Down. So therefore the pressure went up or down.
Down.
If you have less moles, the pressure's gonna.
Less things hitting the walls. So less pressure. Right. Less particles hitting.
If you have less particles.
Do I have the same, did the volume change here? Did I indicate that the volume changed?
No, it didn't change.
Volume's constant here.
Constant, yeah.
So if you have less moles or less particles, there's
Hitting the
not
wall.
as much collisions on the edge.
Absolutely.
So
Pressure goes down.
Mhm.
You wouldn't arbitrarily expect the volume to go up. I didn't pull this from one container to another container.
Yeah. Just the reaction, right?
Right. So yes, you can, and we will talk about things like that. How would that matter? Did we, have we got to anything related to that yet? I think I did talk about at one point where the gas, if the gases are the same, then you can't figure that out, or have I got to that yet? Is that in the equilibrium?
No,
Yeah,
no.
okay, so looking at, this is, so what does this arrow indicate? That's another thing you could figure out from before. That the reaction all goes this way for some
Right.
reason, right? So at some point you have only this, and then at some time point you have only this and no more of this. That's what it is. So what if I formed an equilibrium there?
And then back and forth.
I formed an equilibrium, and now what if I did change the volume and decreased the pressure from one side to the other? Would that shift that equilibrium?
Yes.
So that's where this will come into play more, but we're not into the equilibrium. We're just talking about the rate going one direction.
You're saying changing the volume either up or down?
If the amount of gas in terms of moles
Right.
or molecules changes from the reactants to the products, then by putting a stress on one side of the equation will alter where the equilibrium exists within the overall equation, is what I'm saying. That's called the Chatelier's principle.
Right.
Would the bond do anything? Does it bond?
double bond versus single bond?
Yeah.
Yeah, so in this, is this gonna, can the carbons rotate more in this molecule than in this one?
Yes.
Yeah.
Absolutely. Less rigid. The distance between the carbons here, is it greater or smaller than here?
It's greater than the double bond.
Smaller distance for the double bond, greater for the single
Greater than
bond?
the product, yeah.
See, there are other things you can do just from this, absolutely. You see how, though, when you first looked at it, it just looks like H2 and plus C2H4 goes to C2H6. But there's a whole lot of stuff that you know, and you got to be able to incorporate that into whatever it is you're looking for, let's say in your work, your research, whatever else. Okay. So orientation factor is P, and that's 1.7 times 10 to the minus 6. Is that a higher or a small number?
How can we know?
I don't really have anything.
How can we know?
You don't have an external value, right? So you don't know how, so if we talk about accuracy, you take it and assess it too, but you don't know that because it also depends on the type of reaction. But just looking at this number, is that a large or a small number if you don't assess it in any other way?
Small?
Small number. So that means it has a very low orientation factor, and therefore the rate of this reaction is going to be
Low.
high or low?
Lower.
Lower, right? Based just on that. But as we know, there's a lot of other things going on there, right? So, but if you just look at the orientation factor on its own, then you could say, well, most likely that reaction is pretty hard to get moving, right? So here, which reaction below, so it jumps right into an example, okay. Which reaction below would you expect to have the smallest orientation factor? Explain. So smaller means that it's less likely to interact. That's all the orientation factor is. Which means that I have a lower K and therefore a lower rate of that reaction moving. Okay? So I have H plus I goes to HI, H2 plus I2 goes to 2HI, and HCl plus HCl goes to H2 and Cl2. Which one would have the lowest orientation factor, or the smallest?
A.
So I hear A, and I hear, once again, just like an exam question, what is it? What are you actually looking for here? When I say, so let's take a step back because both would be right depending on what you're looking at.
Right.
That's why you say A and you say C. Only one of them's right, obviously,
Yeah.
based on what it's asking. But if I looked at this and didn't read it right, then I could easily say A or C. Right? So it's saying, here I'm going to say the smallest orientation factor means that it's the least likely to orientate correctly for the interaction to occur. When I have just one H and one I, pretty easy for them to interact and form,
Gotcha.
which would be a higher orientation factor.
Gotcha.
See, and that's here. This is going to be a little high. This is going to be a little bit smaller than this, and this two completely different things. They're not going to interact that well at all. They have to be orientated appropriately, so that would be the smallest orientation factor.
Would B have a smaller orientation factor than A because they're bonded to each other? So it has to break apart?
Has to break, but also just the orientation. So that would be maybe in the activation energy or something like that, this would be harder. But for the orientation, I could have the H2s and H2s hitting each other instead of the HIs, right, more often because they're bigger. So this would be a little bit lower than this because this is 1 and 1. Once they hit, they're good.
Yeah.
And also where they hit. So if I have the two H's and the two I's, they hit in the middle there,
Right.
that would cause a bad orientation.
Or
And
just
that'd be
one
one
each,
that would
right.
lower it a little bit more, yeah. Versus just one each, wherever it hits, presumably it's okay. Oh, they didn't. Okay, just make sure. This one would be the lowest.
Does that mean it's a different color?
Huh?
As well? It's a different color as well. I wonder if that's what they're indicating.
Oh no, it's yellow,
Oh,
green, and
they're all
blue.
different colors.
Oh, are they?
Yeah.
Those just are closer effective. Usually I get like a circle or something that
Yeah.
indicates, or a check mark or whatever.
Oh, that is good.
It's okay, we don't need them. Potential energy diagrams for reactions. So here we're going to look at, okay, so we've already covered these things. If I look at this here, my reactants, my products, I'm looking at the progress of the reaction and the energy. In this case, it just says per mole. Okay, so going from here, NO and Cl2, my reactants, to my products, NOCl and Cl separately. By the way, there's that little symbol here. What does this indicate here at the top there? That's my transition state.
Right.
This is dealing with transition state theory most likely. My energy for my reactants are here. What is this from here up to that point? That's my activation energy.
Right.
Okay, that's all of my activation energy. Then, as I overcome this huge activation energy, at least from the picture, and it looks like 85 kilojoules per mole, I need to get up to here. Then I get this transition, and once I get there, the activated system, it now drops down to the product, but it only comes down this much. So I recover a very small amount of my activation energy that I used to put in. The rest stays in to hold the complex together, meaning that the rest of the complex itself that I formed here is less stable than this, because it has a lot more energy to hold it together. So then energy went into the system. That energy that went in, or the delta H, the enthalpy that I had to put in, overall, the net is going to go from here to there.
Right.
So the only amount I recovered of the activation energy is here. And that just means that I now have products here, reactants here, more energy in this endothermic process. What else can you see potentially happening here? Absolutely, right? If I look at this, I'm thinking, well, wow, this going to here is pretty hard. This doesn't really want to be here. 83, I only recovered 2 kilojoules per mole after getting it over that activation energy. Wouldn't it likely want to go right back and form some kind of an equilibrium where I'm going to have much more of this than this, right? Depending on the situation, the circumstances, how I assess that, how much energy I have in, et cetera, orientation factors and everything else, right? Frequency factors and all that. So I would assume that, hey, a lot of this is going to just go right back this way. It's going to form some equilibrium between this and this. And I'm going to have something like 99% of this and 1% of this after my equilibrium. And just to put that when I use the term equilibrium, I don't mean equal amounts of the reactants and products. I mean that at some point, usually they're in a dynamic equilibrium where they're moving back and forth. The rate, as we're discussing now in this chapter of the reaction, is the same going this way and this way. That's the equilibrium, not the amounts, the rate of the reaction. Hence why we start with rate of reactions, and I think the next chapter, I'm assuming, has got to be equilibrium. It is, okay. Okay, so that gives you some sense of where we're moving towards. Okay, so this is the activation energy here, and this is just the delta H of the enthalpy of the overall reaction. Transition state theory. Once again, we've talked about this pretty much. Essentially, AB forms this AB complex, which then breaks up into CD as products. This part at the top of the activation energy curve, that's where you're in your transition state. Okay. And this exothermic, because the amount of energy of the products is less than the reactants, which means the delta H of the enthalpy is what? Negative or positive?
Positive, or negative.
If it's exothermic, it's negative, because I lost the energy. Right, just to recall certain terms we learned in 101, right? Within the chemical equation, it's a positive on the product side. And for delta H on its own, it's a negative sign because you've lost that heat, or you've put it from the system to the surroundings, if you recall that orientation as well.
Right.
Oh, really? All right, this is almost embarrassing because you guys definitely would know how to, they're just saying plug in the boxes.
Yeah.
All right, we can skip this. Is clearly
Label
reactants,
extract.
activation energy, delta H, and products. I don't think I'm going to give you anything quite that easy on the exam, because I know that you're all much, much smarter than that at this point. Okay, so that does transition us into reaction mechanisms. We are about I think just one lecture behind, and this would be the next lecture. So we have plenty of time to start getting into, this class goes to 25? So we have about 10 minutes. So let's get into a little bit reaction mechanisms, and then we could probably finish this chapter off this week, and then we can start equilibrium.
Awesome.
Okay. Okay. Reaction mechanisms. When we talked about rates, and we were looking for the exponent here, and the exponent, I said multiple times, was something that it was not. What was it not? The coefficient, right? Yeah. Remember, I say these things multiple times, so I think it's fair for me to ask you what I said, because it should just be ingrained, which is why I say things so often, because then when you get home, you're like, oh, you don't even really study that much. You already you just think of what I said over and over and over, right? And ideally, that settles in, and that just makes, now I just have to figure out how it relates as opposed to what those things are. So it did not translate as the coefficient, but the coefficient must be relevant. I mean, right? I mean, how does that work? And what happens is, when you see those chemical equations, what are you really looking at? Do you see, as an example from what we just saw, we saw the activation energy curve. Mm-hmm. When we saw the products and the reactants in the chemical equation, what didn't we see that we see on that chart that I brought up multiple times also?
You see like multiple steps.
You didn't see the transition state?
Yeah.
That was never there in the actual chemical equation. Because what is the chemical equation, what do we call that? The overall chemical equation. Yeah. So that's showing you what you started with and what you ended with.
True.
But did multiple things happen along the way?
Mm-hmm.
Yes, in 101, where did you see that?
The redox.
Thermochemistry?
Right.
Hess's law, absolutely, we saw that in Hess's law. We saw that, you guys already kind of know this. It was just never put in that context, right? That's Hess's law. That's looking at each level and saying what I had to do here, how much energy did I gain or lose, how much energy here, goes up, comes back down. I think we saw it putting together sodium chloride. Okay. Multiple steps, reaction mechanisms. These are just the steps involved going from reactants to products that may not always be seen in the overall chemical equation. So each one of those steps, elementary equations, we'll talk a little bit about. If I looked at the elementary equation, I can actually figure out how the coefficients correlate to that end. But not from the overall, because they're all the individual steps along the way. Okay, so let's take a look at that as a premise of reaction mechanisms. So they consist of a bunch of elementary reactions. The overall effect, canceling things out from side to side, gives you the chemical equation, the overall chemical equation, also noted as the net chemical equation. And that's all you see in it put together. That's why you can't figure out from the coefficients what this exponential factor is, because you're not taking into account the other things that happen. Why do the other things matter, by the way? If I have something, instead of just one step is shown in, say, 3 steps, what would matter in those 3 steps? The rate of what? Each step. What if one is much, much slower in that sequence than the other 2?
Slows down, yeah.
Then that one is going to be the one that's going to indicate the overall rate of that reaction, right? Mm-hmm. Also the one I could probably figure out what this is. Does that make sense? Does everybody see like how that matters? I could develop a bottleneck at some point through multiple reactions. As I go through one really fast and I get to one that's slower, right? You see that in business all the time, right? You're making something, but then at one point something's a little harder to make. And that's the bottleneck, so you can only produce so much at one time.
Right.
And that's what you're always looking for to try to overcome. How do I relieve that bottleneck and open it up as much as possible to produce more? The operations of whatever it is you're making as some kind of a product or service, how you get that service, right? Same thing in reactions for science, right? I have multiple steps. I have one step that's now inhibiting the rest. We saw something like this too. We called it limiting reactant. So we kind of have a sense of how that kind of thing works, right? If I have excess versus limiting, the one that's limiting is going to be the one that's going to give me the maximum amount of theoretical yield, right? Remember that?
So if something was a 0 order and you don't really write it in the equation, then would that mean that it's still slowing the other ones down?
It could, depending on the situation, right? If you have other ones that are much, much faster than that one, then it could, absolutely. But then that all depends what you're mixing. And you're also clearly getting things in these that are not being shown in the overall reaction, which means that they're what? They're canceling each other out, so they don't exist at the beginning or the end. Right? So those things matter too. But I also can't assess this in relation to something that's not in the overall reaction, because it's not there to begin with and it's not there at the ending. So there are a couple other things we need to look at and think about. But these are called elementary reactions. Okay, so these are just the single single molecular events as described of reaction. And of course, that's all related to K. Multiple collisions. So here's the net chemical equation of NO2 and CO forming NO and CO2. Okay. And we're going to set some conditions, so we're kind of fixing K here, below 500 Kelvin, and it takes place in 2 steps. I have NO2 plus NO2. This is step number 1, forms NO3 and NO. And then I have to have something with CO here, right? So I have NO3 here binding the CO, forming NO2 and CO2. Now, when I look at this, I say, okay, up here, I don't have NO2 in here,
Right.
and I don't have NO3 in there.
Well, they cancel.
But the NO3 cancels out here, and one of the NO2s cancels out there, leaving me with NO2, CO, NO, and CO2. So it happened in 2 steps. But you only saw this step previously. So you don't realize that actually NO3 is part of this equation, and so is other things, right? What else is in there? NO3.
Yeah, the
NO3 is
NO2.
the only thing that's not
The extra NO2?
the extra NO2. But you know there are a bunch of NO2s there. The reaction just shows in a
Just one, right?
coefficient ratio based on the conservation of mass, you only see 1. So these are the things that happen here. So now what do I need to assess? Which one happens first or faster, which one's slower? If this one's really slow and this one's really fast, then this is where I worry about the rate. Because no matter how much of this I make, this is moving quickly. Or what if it's inverse? I make a whole bunch of this and now this is slowing it down. So then I only worry about the rate of the overall reaction based on the one that's the slowest. And if I do that, then I can assess, let's say here, then I would have a first order NO3 and a first order CO. However, I can't have NO3 there because it's not in my overall equation, so I have to manipulate that in order to get something I do have in my overall equation to mix, and then I'll show you how to do that as well. But you see the general sense, and now how the coefficient does play a role in the exponent, just not in the way that you thought when you first saw it, which would just be, oh, it's my overall equation, coefficient fits right there. Okay. Elementary reactions, each one. And these are my, what we call intermediate chemicals, or short-lived ones. Those are just things not seen in the overall reaction. How do I know this happens? That's the next thing. So this is also really, really important as we move forward. How do I know, can I have multiple different mechanisms? Let me start with that. Let's kind of put this in context. Is this the only thing that can happen? I could make up all kinds of things that would show something where I get this as an overall equation, right? How do I know which one's right? Thank you. It's absolutely experimentally, right? Remember we talked about how you have to figure out things experimentally? Experimentally. The other thing is, if I wanted to say, so experimentally, can I figure out what the rate law is on this one? If I had experimental data, what am I trying to figure out here?
Exponent, yeah.
I could figure that out. And then I could match it to one of these and say which one of these, using now the coefficient, of course, right, as the exponent, matches what I know experimentally. So I could figure out then which one is the slower rate, or the one that controls the overall rate of the process. Okay, and with that, I'll leave you there, and we'll pick this up and try to finish this chapter off on Thursday.
What are the reaction intermediates?
What's that?
The intermediates are the excitator ions?
The intermediate are the,
Excitator ions?
Spectator.
Excitator ions?
well, they're not ions. They're spectator, you could say compounds, you could call it a spectator chemical. I mean, you could use a variety of terms, but the analogy, I think, is what matters to what you're asking.